Intermolecular forces are any attractions between any molecules. In this context of what we'll be doing in this chapter, we'll be talking about like molecules with molecules of their own kind. But in the solutions chapter, we'll be talking about intermolecular attractions between different kinds of molecules. So the intermolecular forces are important because they determine most of the properties of a substance. So state, for example, is determined by intermolecular forces, and it's a balance of both the strength of the intermolecular forces and the kinetic energy of the molecules. Now, something that maybe is easy to miss in the description of intermolecular forces is that they are all attractive. It turns out that you can't have intermolecular forces that are repulsive between molecules. And the reason is when two molecules repel each other, it's usually some sort of Coulombic interaction. So I have a like, right? Opposites attract and then like charges repel. But when we're talking about molecules, for example, HF. So two hydrogen fluoride molecules. Remember, we talked about dipoles, and fluorine's more electronegative than hydrogen. And so I get a positive dipole on this end and a negative dipole on this end because the fluorine, being more electronegative, draws the charge towards itself. So if you think about the dipole being written like this, if I bring a second HF molecule next to it like this, it's clear that this will repel because these are the positive ends. But what the molecule will do is it'll flip around. And so it'll basically turn around to be facing it like this so that there's a force of attraction between the hydrogen of one molecule, that would be this one, and the fluorine of the other molecule. So even though it's possible to have repulsive intermolecular forces, because molecules are free to move, they almost always turn those into attractive forces. The only time it might not work out that way is if it gets locked into a lattice where there's a repulsive force, but normally those things don't form. All right. Now, if we think about what intermolecular forces do, and because they're attractions, when you think about the energy it takes to transition from one state to another, remember we drew a diagram where we had the solid, then the liquid, and the gas, like this. If the intermolecular forces are stronger in a substance, then these transitions, rather than being maybe low in energy, right, ends up being higher in energy. So in the substance I'm sort of illustrating on the left, weak intermolecular forces. On the substance on the right, it's strong intermolecular forces. It takes more energy to make the transitions happen because the molecules are more strongly attracted to each other. This means both higher boiling points and higher melting points, and it also affects a number of other properties of the substance. And again, just to reiterate, changing temperature is changing the other factor in the state of the substance. By changing the temperature or increasing the temperature, we begin to overcome the intermolecular forces of attraction. So what's sort of the one thing that you can look at to understand what intermolecular forces a substance will have, right? And it turns out the answer is structure. Intermolecular forces, and I'm just going to abbreviate it, IMF, is determined by structure. And this is where it becomes important that you understand how to draw a Lewis structure. So if we want to know the structure, right, we're going to do Lewis structure. And then beyond that, if we want to know whether or not something has like a dipole, which is one of the intermolecular forces that we talk about, then we have to look at electronegativity, and we also have to look at shape. So when we're talking about Lewis structure, we're just talking about bonds, but then further we have to go to Vesper theory. And then we're looking at shapes and dipoles. Now, it turns out that's not the only thing that's involved in the analysis of structure. It'll also come down to like how many electrons it has. And it'll also come down to other features like something we call hydrogen bonding, which if you've taken some biology courses, you've probably heard of. So this first force of attraction is, I don't believe, covered in your book, but it's called ionic polar interactions. So you imagine a sodium ion, but it illustrates the idea of the properties of intermolecular forces. So sodium ions are positively charged, right? And if you look at the electrostatic potential map of water, that's what this is down here, we show the red shows the negative end of the dipole, and the blue shows the positive end of the dipole in the molecule. So when a sodium ion is in the presence of water, what ends up happening is the negative end of the oxygen begins to touch onto the sodium ions, and then eventually surrounds it, and roughly speaking, in the process of what's called solvation, where ions are surrounded by water molecules and water is the solvent, you get 1, 2, 3, 4, 5, 6 different water molecules surrounding each sodium ion. Now, if you remember from your VSEPR theory, 6 groups on a central atom gives us an octahedral coordination of water molecules around a central sodium ion. This is a key thing that you'll see in the short video that I'm going to play, where we look at the process of a sodium chloride crystal being dissolved by water on a molecular atomic level.
An ionic solid dissolves in water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively.
Now, these are the chloride ions. Remember, this is the positive end. Remember, chloride in sodium chloride is the bigger of the two ions because it gained an electron. So this is a negative ion.
Charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These
This is the beginning of the coordination.
interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
Now, this is a relatively strong type of intermolecular interionic force. I put numbers in here. These are sort of ballpark numbers, but it's one of the strongest ones. This is one of the reasons why water is so good at dissolving so many ionic compounds. Ionic interactions are relatively strong, but water, because of its very high polarity, has the ability to separate the ions in a solid. And when that happens, it's the negative end that attaches to the cations, and then the positive end attaches to the anions. So let's talk about dipole-dipole interactions. Dipole-dipole interactions occur when you have polar molecules, and the dipole of one molecule can interact with the dipole of another molecule. This has both effects in the solid state, this would represent the solid, the liquid state, and even in the gas state when the molecules are far apart from each other. The intermolecular force of attraction will still be there, although in the gas state it has relatively less effect because the energy of the gas is higher than that of the liquid. So what affects the strength of a dipole-dipole interaction, right? It's the difference in electronegativity between the bonds and how symmetric the molecule is. So if you have a large difference in electronegativity in the bonds, typically speaking, the dipole-dipole interaction will be stronger. But if the molecule is symmetric, it can also be nonpolar, in which case the dipole-dipole interaction is non-existent in those molecules. So really, for dipole-dipole, we look for bond polarity, and that's doing electronegativity difference, and symmetry. And by symmetry, we look at the molecular geometry, the shape. So I'm just describing these sort of superficially at this point, and then what we'll do as we get into further along into this session, we'll talk about specifically looking at examples and how you tell the difference, and then how you make comparisons between molecules. This is a short video clip showing how intermolecular forces of attraction assist in the formation of the liquid state.
Hydrogen chloride molecules are polar. When HCl molecules in the gas phase are cooled, the kinetic energy of the molecules can no longer overcome the dipole-dipole forces between them. The opposite ends of the molecules attract each other and coalesce to form a liquid.
So, dipole-dipole interactions are part of a group of intermolecular forces known as van der Waals forces. So for a dipole-dipole interaction, we call this a permanent dipole or fixed dipole interaction. But what you have to remember is the electrons in an atom are not bound to be in one place, and so they actually can be moved around. The wave function can be altered in such a way that they appear in different positions in the molecule. So there's also something called an induced dipole. An induced dipole is a temporary dipole. And it's created by the shifting of electrons. So what does it look like, right? An induced dipole. So this is what we're calling a dipole-induced dipole. It looks like this.
On average, the electron cloud of an O2 molecule is distributed symmetrically across the molecule. The molecule is not polar. A water molecule, which is polar, repels the electron cloud, causing it to be asymmetrically distributed and thereby induces a dipole in the O2. This shift allows O2 to be weakly attracted to the water molecule.
So you can see the shifting of the electrons in the oxygen molecule. Even though it's nonpolar and doesn't have a dipole on its own, it can be induced to have a dipole when the negative end of a water molecule comes next to it. That creates the dipole, which causes oxygen, right, O2, to be slightly attracted to the water molecule. So as simple as this idea might seem, I mean, it's important because this is how water gets oxygen in it. And this is why fish, for example, can breathe the oxygen that's in the water. It has a high enough concentration that the fish can extract it using their hemoglobin. And it only has that because water is able to induce, because water's strong polarity is able to induce enough of the dipole in the oxygen that it dissolves in the water to a high enough concentration. Now, we also have just the straight induced dipole, which is known as a London dispersion force. So what is the induced dipole? So we can understand pretty easily how dipoles can induce dipoles by pushing electron clouds around. But it also turns out two molecules can get together that are nonpolar, and whenever they do, they induce a force of attraction between each other called an induced dipole.
An iodine molecule has, on average, an electron cloud that is symmetrically spread over each iodine atom. I2 is not polar. The attractions or repulsions between the atoms of I2 molecules can distort their electron clouds. Dipoles can thereby be induced momentarily in neighboring molecules.
So there's a dipole-induced dipole, and then there's just a straight induced dipole. So even two nonpolar molecules can shift the electron density enough that they become attracted to each other. Now, let's think about this real quickly. I'm going to draw a couple of different things up here. We have F2, it's a gas. Cl2, gas, room temperature. Br2 is a liquid. And I2 is a solid. So you notice what's happening here. As you go down the halogen group, this is the 7th group on the periodic table, or 17th group, depending on which you've bought into. Going down this column, right, we go from gas, gas, liquid, solid. Now, quick question or quick thought, right? How does the intermolecular force vary if at room temperature it goes from being gas up here to a solid down here? How is that intermolecular force varying as you go down the group? And for iodine to be a solid rather than a gas, it must have higher intermolecular forces. That is, the kinetic energy at room temperature that's available to the molecule isn't enough to separate them from each other. So this trend that we see for fluorine through iodine occurs because of increasing intermolecular force. Well, what's the difference in these, right? They have the same number of valence electrons, but the answer is the difference is in the number of total electrons that each atom possesses, or each molecule possesses. And the strength of the induced dipole varies with the number of electrons. So if you have more electrons to move to one side, you can create a bigger dipole. So it is related to molar mass, but it's really mostly related to the number of electrons, okay? And then the other thing that's important about an induced dipole is its surface area that it makes contact with. So if you think about why that might be, right? Think about Velcro. What does the inside surface of Velcro look like? Well, I'm almost embarrassed to say this is a really cool image that I stole from Pinterest, which I don't use, right? Sounds like I'm doing this for a friend kind of thing. Yeah, it's an electron micrograph of Velcro. And so what you're looking at here is the structure of Velcro. One side, this is the rough side, okay, has hooks on it, and each of the hooks has been broken. I don't know exactly how they get that to happen. This may just be one segment that's entirely uniform. And the other side has little woven loops on it. Now, one hook of Velcro has very little force in which it could hold something. So this is the equivalent of having small surface area. Hydrogen molecules, for example, H2s, have very small surface area. Helium atoms have very small surface area. When they contact, that's where the intermolecular force is created. And as a result, they have very weak intermolecular forces. But as molecules get bigger, it's kind of like Velcro. The more places you can have, even though the intermolecular forces are weak, the more places you can have these weak intermolecular forces, the stronger the net effect becomes. So it also turns out that the intermolecular force, in addition to being determined by the number of electrons in the area where the contact's at, it also has to do with how much contact the two molecules make. This is why, for example, fats, like lard, is a solid at room temperature. It's made up of very, very long chains of carbon, even though it's nonpolar. We know it's nonpolar because if you try to dissolve, for example, butter or oil in water, right, those are related to fats. They don't dissolve in water. Lard doesn't dissolve in water. And the reason is the intermolecular forces between the water and the lard are very different. But then lards, even though it has a weaker intermolecular force type, the molecules have molecular weights in the hundreds. And as a result, they have overall very high intermolecular forces of attraction, and that's why they're solids at room temperature, like I was saying. So we have van der Waals forces, dipole-dipole, what we talked about on this slide. That's one type of van der Waals, and that's a fixed and permanent dipole. Then there's dipole-induced dipoles. These are temporary dipoles caused by shifting of electrons, induced by another dipole. And then there's the induced dipole, and this is just interactions between electron clouds which eventually force a molecule to have a distortion in the electron cloud, which then allows them to be attracted to each other. And this one is the one that's a little trickier to look at because it depends on the molar mass and also the surface area of the contact. In general, longer molecules have more contact surface area than do small and bulky molecules, and so they will have higher intermolecular forces. Now, the strongest intermolecular force is known as hydrogen bonding. Hydrogen bonding also depends on structure, but it only occurs very specifically with 3 atoms and their bonds with hydrogen. So one is nitrogen, the other is oxygen. This is the one we see the most of in biology, biochemistry, and the last one is fluorine. Now, remember, we talked about when 2 molecules get together. So, for example, HF, and they form a bond. The bond gets distorted, and it shifts the electron density to one side. And as a result, this part of the molecule becomes extremely positively charged. Well, in HF, and then HO bonds and HN bonds, what happens is that force of attraction is so strong that it strips the hydrogen of its electron cloud. And there's essentially the backside of the hydrogen is exposed for another pair of electrons to come in. So what this does is cause the hydrogen to go seeking out pairs of electrons. In other words, it'll find another lone pair. Remember in HF, right? That's my HF bond. It's very strongly polar in this direction. There is a positive charge on this end, which is then attracted to a lone pair of electrons to cover this end of the molecule up. So I kind of always made the analogy of you're in bed and you're with your significant other, and they roll over and they take the blanket away from you, right? What happens to your backside, right? It gets cold. So what do you always look for? You go look for another blanket to try to cover it up. Hopefully you didn't answer, you go to somebody else's bed. But like I'm saying, you go look for something to cover your rear end and warm your rear end up because it gets cold when it's exposed like that. So there's a big shift in the electron density, a very large positive charge on this end, right? And a very large negative charge on this end. And then there's going to be a fluorine over here, and that fluorine is attracted to the loss of electron density over here. And it's the strongest of the intermolecular forces. What I didn't mention on the previous slide was that induced dipoles are typically 1 or 2 kilojoules per mole. So they're weaker than dipole-dipole. And then hydrogen bonding is 10 to 40 kilojoules per mole.
Oh, groovy, baby. Yeah.
I'm sorry. I forget, I get sounds in here sometimes. Okay, so here's another interesting graph. Okay, let's take a look at a series of molecules. There's H2Te, H2S, Se, and H2S. And you'll notice this is third, fourth, fifth period. And this is where you would expect water to be. Okay, H2O would be the second period element. And so if you were drawing a line, trying to get a good idea of what this graph looks like, you're going to be giving it a little bit of curvature. You might expect it to be right around here. And what you're seeing here is what you expect to see as the molecular weight goes up and the induced dipole goes up. So H2Te, even though it's not as polar as H2S, it has a much higher molecular weight. And the result is it has a higher boiling point because the more electrons something has, right, the bigger its induced dipole. So let's look to see how hydrogen bonding affects this diagram.
A plot of the boiling points of the group 6A hydrogen compounds shows a trend. Based on this trend, we would expect the boiling point of water to be here. In reality, H2O's boiling point is much higher. This is a consequence of water's stronger hydrogen bonds.
So it's hydrogen bonding, right? So you're noticing the effect, and by the way, they kind of exaggerated and drew it down here. It's really right about here. That you would project that out, you can see the shape of the curve. Anyways, this is the kind of change you expect to see in the induced dipole. That water has a boiling point almost 200 degrees Celsius higher than you would expect it to have. Implies the relative strength of the hydrogen bond relative to the induced dipole. So the hydrogen bonding effect is really large. So if you look at these two isomers of each other, this is ethanol. It has 2 carbons, 6 hydrogens, and an oxygen. Well, this is oxygen and hydrogen. So this part of the molecule, this has hydrogen bonding. On the other hand, in dimethyl ether, you'll notice that this molecule is polar. It has a dipole going this way. It's polar, but doesn't have the hydrogen bonding, because what's important in hydrogen bonding is the hydrogen is bonded to the other atom here, oxygen. So even though this has hydrogen in it, it's not bonded to the oxygen. It doesn't have hydrogen bonding. The difference in boiling points, even though they have the same molecular weight, is almost 100 degrees Celsius. Not as much as you see here, but very significant nonetheless, right? It's a much higher boiling point to have hydrogen bonding than to not have hydrogen bonding. So to summarize, we have van der Waals forces, which include dipole, induced dipoles, and then dipole-induced dipoles are also in there. Those are possessed by all molecules, because remember, it only requires that they have electrons, right? So the ability to shift electrons around, which exists with every substance, is all you need to have that. And so everything has an induced dipole. Now, the other thing that we are going to you look at then is hydrogen bonding. And hydrogen bonding is the strongest of the intermolecular forces. But for induced dipoles, one of the things that you have to understand is that those get stronger as the molecular weight gets higher. And that's not just because the atoms get bigger, but it has to do with the surface contact area that the two molecules could make. So two molecules of the same molecular weight, one which is long and skinny versus one which is sort of short and round, the long skinny one can lay next to another long skinny one to make better contact. And so stronger intermolecular forces also go with the longer molecules.